Okay, so it's a great pleasure to speak on higher Teichmüller theory and geodesic current.
Okay, well, thank you very much thank you very much for the invitation. That's the first thing. But it's too bad that Ludwig is not here, because this reminded me of when he came to Zurich to give a talk. And it was actually a rather important talk, but you know, and he prepared his slides and everything. And then we couldn't succeed in having the beamer turn on. And so we went to get another portable beamer, and then we didn't succeed in having the one turn on. And then we thought, okay, fine, we can just have the old, because you know, he said I can print out the slides and then I can put them on overhead projector. And we did that, and well, we tried because we didn't succeed in having the slides print out. And then it turned out that the screen was not coming down. I mean, the whole thing was that this is in a polytechnic school, okay, all of that. So you had to postpone the talk to the next day. So I thought that this was his revenge somehow. Anyway, so I have to say that my talk today should have been before the previous one. So this is in some sense not a preparation to Mark's talk after mine, but not to say a lot of things that he will somehow use, and I think that many of the things that I'm going to say would have been very nice if had been said before the previous talk. So anyway, so this is joint work with Mark Berger, Anne Pavot, Beatrice Pozzetti, and so the general thing that I'm going to talk about is, you know, some aspects of higher Teichmüller theory, generalization of the higher Teichmüller theory. So in this talk, I'm going to first talk about some aspects of the classical Teichmüller theory. Then there is going to be a structural theorem for geodesic current. And then I'm going to talk about what I realize I should call by now classical Teichmüller theory, higher Teichmüller theory, because Vladimir and Alessandra are going to talk about the new higher Teichmüller theory. So this is by now is old. Okay, so let me just say a little bit about Teichmüller theory, even though probably this is embarking on the wrong tree here. But still, so Teichmüller space is Teichmüller theory is one of the few, it's one of those theories in which there are influences from many fields that come from, so on a kind of an equal ground. So the most obvious, of course, are again complex geometry, hyperbolic geometry, the theory of discrete groups, algebraic geometrical dimensional topology, dynamical systems, the theory of Lie groups, and topological quantum field theory, string theory, and so on. So, but exactly because there are all these different inputs, all these different ways of thinking about Teichmüller space, I want to tell you the way I think about it, so that the way we think about it, so that at least we know what we are talking about. So we are going to start, for the moment, sigma is going to be a closed oriented surface of genus G, greater than 0. For the moment, we are going to, sigma, it's always good. Yeah, okay, for the moment, we are going to assume that there are going to be no punctures, okay? Then later, but it's only for simplicity, because some of the things I'm going to say hold in general. So, Teichmüller space was defined as the space of conformal structures on the surface up to the action by orientation preserving diffeomorphism, and do the uniformization theorem. This is the space of complete hyperbolic structures. And the way there are several characterizations of Teichmüller space, and one of them is the space of representations of the fundamental groups into PSL to R, which are discretely injected up to the action of up to conjugation by PSL to R. Then another way to look at this Teichmüller space is one connected component in the representation variety. And in fact, which connected component actually comes from this third characterization. So one can define an invariant on the representation variety that takes a certain number of values in the case of in which we put ourselves, so there are going to be 4G minus 3 values, and Teichmüller space corresponds to the value of this invariant, to that maximum value of this invariant. This is called the Euler number. And fourth is all representations such there exists a gamma, so a row equivariant map from S1 to S1. This S1 here is the boundary of the fundamental group, and this S1 here is the boundary of hyperbolic space, on which PSL2 is the isometry group. And if you find such a map, so being a representation type of the space is equivalent to saying that there is such a map that is Borel, row equivariant, and monotone. Okay? And so what is we're going to talk about today about compactifications. We're going to look at various compactifications. That is what I'm going to be talking about, and this is what Mark is going to be talking about afterwards. And so one of them is Thurston compactification was mentioned to some extent, was also in the previous talk. So what was Thurston looking for? Well, let's say that if you have a fundamental group of hyperbolic surface, this acts on the hyperbolic space, and the action extends continuously to the boundary. And then you can also classify isometries in terms of the dynamical properties of the elements of the group. In other words, how many fixed points, relative fixed points, and so on and so forth. So Thurston's idea was, well, okay, let's look at the mapping class group, and this is the automorphous group of the fundamental group modulo, the ini-automorphous, and this acts on Teichmüller space. Teichmüller space happens to be, it's proven to be homeomorphic to a ball in R to the 6G minus 6. So, and the action, and in addition, as an inspiration, the mapping class group of the torus, of the one torus, is a cell 2G, and the Teichmüller space is the Abraham space, can be identified with the Abraham space. So somehow, Thurston's idea was, well, just like the fundamental group, a universal 2Z, acts on the Abraham space, it continuously extends to the boundary, and I can classify the isometries by looking at fixed points. Can I try to do the same? So I have Teichmüller space, that is this R to the 6G minus 6. Do I find a compactification that such the boundary is a 6G minus 7 sphere, so that the closure is going to be a ball, a closed ball. It's going to be the ball in 6G minus 6. And at that point, I can use Bragg fixed point theorem. I know that there is a fixed point, and I can try to classify this. Okay, this is what he wanted to do, and this is in fact what he did. Okay, so in fact, in his compactification, so those are the properties that he wanted. So he wanted so that the boundary is the sphere, so that the closure is the closed ball, and then you can extend continuously the action. You have an action by homeomorphism now on the closed ball, and then you can try to classify the mapping classes by using Bragg fixed point. So this thing I never know what I want to say afterwards. Well, okay. So probably I want to look at right. So one thing that you get once you have the hyperbolic structure on your surface is the concept of geodesic, and you have the concept of length of a geodesic. So we're going to think of, so C is going to be the homotopy classes of closed curves, and if I take a hyperbolic metric, I can define the length of a curve, the length of a homotopy class of curve with respect to this metric. And this is nothing but, okay, the length of the unique geodesic that is in the homotopy class of this, well, that is in this homotopy class, okay? So that means that I can define a map that from Teichmüller space, and so to a equivalence class of metrics associates a projectivized length, okay? Exactly in this way. And this map has a property that, this is a cursor proof, has a property that it is an embedding, and the image is compact. And in fact, also I have the properties that we had before. It means that the mapping class group acts, the mapping class group extends to the boundary and acts, and the boundary is a sphere. And so I call this the Thurston polynomial compactification because this is what Thurston did, but then I think it was in the 80s, but then Bonahon came along and he identified very precisely what are these, he identified what is the boundary of this compactification and the compactification. And this he described it in terms of geodesic currents, measure laminations, and intersection numbers. And I'm going to define all of these things. So what is a geodesic current? Geodesic current were initially defined to try to try somehow to study homotopy classes of curves. And let's think for a second what happens if we take a closed geodesic on the surface. Then we lift it to the universal covering, and we have in the universal covering we have a discrete subset of curves. I mean, a discrete subset of that are all the inverse image of this project. And discrete in the compact topology of the space of geodesic, and then because I do not want to have. I do not want to allow geodesics to wrap around more than once. I need to think of somehow, I need to give some multiplicity to a simple closed geodesic. What is the reason? The reason is that, geodesic that do wrap around more than once exist. So you cannot really eliminate them. But when you go and look at the universal covering as to whether it wraps around once or twice or 10 times, it still is going to be exactly the same on the universal covering. So you want to eliminate that, but you want to say, okay, to each of these things I'm going to give a multiplicity. A multiplicity corresponds to how many times it wraps around. Okay, so at this point I can think of this simple closed geodesics as Dirac masses with some multiplicity. And a geodesic current is is nothing but a generalization today of this from Dirac masses to measures. So let's see, a geodesic curve. So on sigma is a quasi-Pradon measure on, so geo sigma tilde is the set of geodesic in the universal cover. Okay? So let's see what are examples. In what I'm going to be saying is going to be convenient to identify a geodesic in the universal covering with, so the universal covering I'm thinking about as the Poincaré disk. So a geodesic I can identify by giving the initial point and the end point. So a geodesic is just a pair of points in the boundary hyperbolic space without the diagonal. So they have to be distinct points. And so, okay, what is an example of such a geodesic curve? Well, this example here is exactly what I was talking about. If you take a closed geodesic and then look at the universal, you lift this closed geodesic to the universal cover, and then this you can identify with, so gamma is going to be the outside hyperbolic gamma, represents this geodesic, and I'm going to look at the initial endpoint. And then this delta C is going to be just a Dirac mass of all the possible translates. And the support of this measure is of course just the lift of the thing. So this is one current geodesic curve that is going to be actually important for us. Then the next one is the so-called the Lubin curve that is also extremely important for what we are going to say, at least as a, I mean, it was important in for Thurston-Bonneman's theory. So Lubin current is the unique PSL2R invariant measure on the space of geodesics on the hyperbolic space. And so what is, and how can I describe this? I can actually give a very, very explicit description, which is as follows. So there is a natural orientation in the boundary hyperbolic space. And hence, if I give you, even if I think of my drawing are going to be on the Poincaré disk. So on the Poincaré disk, if you take 2 points, it's not clear what is the interval you're talking about. But once you fix an identification with the real line, then okay, you can talk about an interval. And now I'm going to take 4 points on the boundary of the hyperbolic disk, and I want to say what is the measure of all the geodesics that have the beginning point in the interval TA and the end point in the interval BC. These are all the geodesics. And this is going to be the Lubin current, and that is the logarithm of the cross ratio. The cross ratio ABCD is defined as A minus C times B minus D divided A minus B times C minus B. So this is always positive, which means that the Lubin measure is also always positive. And then the third example of geodesic current that is very important for us is going to be the geodesic current that come from a measure lamination. Measured geodesic lamination. So what is a measured geodesic lamination? Consists of 2 objects, lambda and m. So lambda is a closed subset of the surface. There is just a union of closed geodesics. Disjoint simple closed geodesics. And m is going to be a transverse measure. So for every arc that intersect transversely the leaves in this lamination, I'm going to give a measure. And that's, so these 2 data are exactly the data that, of a measured geodesic lamination. So what is a geodesic current associated to this? Well, I'm going to take the geodesic lamination, I'm going to lift it to a geodesic lamination on the universal covering, and that is going to have the same properties. So it's a closed subset of the hyperbolic plane, union of disjoint simple geodesic with a transverse measure. And the associated geodesic current takes all the is it A, B, C, D, and I want to look at what is the measure of all this things. So what I'm going to do again, I'm going to just cut, I'm going to consider an arc, and I'm going to measure this arc. Okay? And okay, so these are so this was, I said that the important objects were geodesic currents, measured geodesic laminations, intersection number. So what is intersection number? Well, we know that if you have two geodesics, if you have two homotopy classes of curves, the intersection of these two homotopy classes, the infimum of the intersection of all curves, all various possibilities in this homotopy class. And what I want to do, I want to define, if I have a current, I want to define the intersection in such a way that when this current is the current that was generated by the simple closed geodesic, I have exactly the topological intersection number. So in order to do this, I'm going to look at pairs of geodesics that intersect exactly once. Exactly means that they intersect transversely. Okay? And now this space fibers over the hyperbolic space. I mean, to any pairs of geodesic and associated point where they intersect. And PSL to Z and PSL to R and any lattice acts probably discontinuously. So I can talk about the Bovell fundamental domain for the action. And I define the intersection of these two geodesic currents as the measure, the intersection mu and mu is the measure, the mu times nu measure of this fundamental domain. Okay? And so if it's very obvious that if you have the geodesic currents that were associated, corresponding to one simple closed geodesic, this is exactly the topological intersection number. And this intersection number is 0 if and only if this geodesic is simple. And the other thing that is very nice is that the Liouville, the intersection number of the Liouville measure with one of these geodesic current associated to the simple closed curve is exactly the hyperbolic length of this simple closed curve. This is actually very easy to prove. I mean, it's really all you need is the definition of the Liouville measure and the definition of, chasing out the definition of the intersection number. So it's actually nice. In fact, I was planning to do it if I hadn't been that we started a little late. So, okay. So now, what? So I said that the Bonahon can actually completely describe geometrically what is this. So the Thurston compactification. So in fact, what he did, he proved that if you look at if you take a current, you look at the space of projectivized currents associated to that space, and you can associate the intersection. You can associate the function, projectivized function, that will curve associate the intersection number with this curve, the intersection number of this measure, this current with respect to that curve. And this map has the property that the image contains Thurston's compactification. And in fact, more than that, not only contains Thurston's compactification, but that the boundary of Thurston compactification corresponds to the geodesic currents that actually come from measured geodesic laminations. So Thurston's compactification consists of geodesic currents, and the boundary consists of those geodesic currents that come from measured geodesic lamination. And the way to go from geodesic currents to Thurston's compactification is via the intersection number, basically with the UV measure, with the UV current. So at this point, it's clear that if we want to say something about this Thurston compactification, maybe in a higher, maybe in more general situation, then having a structure theorem for currents is going to be useful, because we are going to land in this space of currents. So it's going to be good to know what we can do with that, whether there is a structure theorem for currents.
So can you say again
Yes.
how you define the intersection? I think I kind of got lost in of two currents.
The intersection of two currents, you're going to look at the, this I can take here. Right. So we are going to look at the space of geodesics, pairs of geodesics that intersect in one point. Okay? They intersect, either they do not intersect or they coincide to intersect one point. We're looking at those intersect one point. And then we have the fundamental group of our surface acts properly discontinuously on this set. Because it acts properly discontinuously on the upper half plane. And the upper half plane is smaller than this. So there's fibers over the upper half plane. So there is a fundamental domain for this action. There is a Bohr fundamental domain, and hence I can just hit it with my measure and see what the measure is. And that is going to be, so yeah, that's the definition.
Each within the matrix. Okay.
Okay?
Yeah.
This is a subset of this quotient, this product space.
Yeah.
Okay? Right. And now we want to see somehow how we can decompose currents, if we can find a structure theorem for currents. Like that. So let's say just what I said before, that that the first example of current was the example when you had a simple closed curve, and then we generalize this somehow to a current that is just a run-on measure. And so what will be hopefully clear later is that in some sense geodesic currents behave like a hyperbolic matrix, but behave like hyperbolic matrix that have the potential of being degenerate. That means hyperbolic matrix where geodesics might have length of 0. Okay, we'll see what this means. But this is one thing somehow to keep in mind. And because of what I said before, the example with the Lewis measure, that the Lewis measure of the Lewis current of mu and delta C, this is the length of C. So in some sense, I put it right here. The intersection, okay, there we go. The intersection of the Lewis current with the simple closed geodesic is the length of the simple closed geodesic. Okay? So I can think of currents somehow as length in some sense. And the other thing is that somehow this geodesic, that if you have a current mu, these geodesics that have 0 length with respect to mu, arrange themselves nicely in the surface. And this is something that was observed by Berger and Pozzenti already for length. So let's see what that means. So we take a current, and I want to try to decompose the current. So I'm going to look at the support of this current, and I'm going to try to figure out what can I say about this support. I mean, how can this support be? Well, here is how. Oh, forgot to tell you the first thing. Yes, in order to do that, I have to start talking about what they are called special geodesics. What are special geodesics? Mu special geodesics. I have a current, and a geodesic is mu special if two things happen. One is the intersection with mu is 0, which means that the length of this the length of this closed geodesic C with respect to mu is 0. And the other one is if I have a geodesic that crosses my geodesic, then this one has to have positive intersection with mu. So now it's obvious. Two things are obvious. One is that a mu special geodesic is simple because because it cannot intersect, because of property 1. And that if you have special geodesics, these cannot intersect because of property 2. Because if a geodesic is special, that means the intersection with mu is 0. So if I have, but also if I have anything else that it crosses this, its intersection with mu has to be positive. So whatever it crosses cannot be a special geodesic. Which means if you have a surface, you can have, use G, you can have at most 3G minus 3 plus P special geodesic. So let's see here what would be the special geodesic. I could have one here, and one here. Okay? And what is nice about
Wait, so these are special for which current?
these have decided they're special. Whatever. Yeah.
Okay. But
Yeah.
if mu was like delta of C double prime, what does it mean? And I'm just kind of.
So C is kind of a component of the current, right?
No, C is just, the closed geodesic C.
I see. So if mu were the current of the lamination, then C would be.
Mu is your current. Sorry, I forgot to write the C. A closed geodesic C is mu special. If its length, basically if it does intersect the support of mu, that's really what it is.
What's the, so if the measure is like delta of A for some simple closed curve,
Yeah.
the first condition is just something that doesn't intersect that curve.
Right.
But what about the second condition? I don't.
The second condition says that
A is positive.
the second condition, let's see.
It probably would be better to have like not just a single closure, but one like decomposes your surface into a bunch.
Right. Let me just give you an example of the thing. So let's say that we look at this set of special geodesics, okay? And
Shouldn't there be two more geodesics on the figure?
I'm sorry?
Shouldn't there be two more geodesics on the figure in the plate?
Depends on your measurement.
The number of simple closed curves.
I didn't say that there are exactly as many. I said that there are the most.
Oh, so in number 2, when you say it intersects transversely, you mean
Yes.
it intersects.
Intersect, absolutely.
It intersects and it's transverse.
Yeah. Sorry. Yeah, I meant intersect. Yeah, that's okay. And so what I'm saying surface into subsurfaces, and the boundary of these subsurfaces are special geodesics. Okay? So for example, in this case, the decomposition would be and then there is another piece. Okay? And all the boundary components are all simple geodesics. And what you get, so the structure theorem is the following. Say that you have a current. Let's look at the support of this current. What can you have? Well, you can have perhaps some special geodesics. So this delta C, perhaps not. I mean, we don't know. I mean, this lambda C could be equal to 0. And then we have other pieces. And what are these other pieces? These other pieces, just when you look at the way the intersection is defined, these other pieces are such that somehow the measure is supported on each of the, is supported in these subsurfaces into which the surface is defined by cutting it over along these special geodesics. Okay?
Do we assume that the number of geodesics is finite here?
What?
Do we assume that the number of special geodesics is finite?
It is finite.
Is it an assumption of the theory?
No, it's not an assumption, it's a consequence of the definition.
But how then?
Because you cannot, two special geodesics cannot intersect.
But it seems that your E sub mu was defined only in this case, on the previous slide.
What do you mean?
Because in the definition it was asymptotic. It can be anything but
Sorry, infinite is wrong. This should be finite.
then it is undefined. What does the theory
But
mean?
it's finite is not because I want it to be finite. It's finite because it is. Because
You
it's a
said
finite
it had less
genus
than
with a
3G
finite number of,
minus
I'm sorry?
You said it had less than 3G minus 3 elements, right?
Plus P. It depends on the genus. I mean, we're talking about homotopy classes.
But your theorem doesn't say anything about homotopy classes, you see? The set of special geodesics, where is the homotopy classes? What do you mean?
Well, they're closed geodesics. Okay. How many closed? How many non-intersecting? Okay. How do you want to? Well, this is you're going to have ultra-finite number.
It is another theory.
It is. It is. Depends really. The number of special geodesics depend only on the number of, at most, on the genus and on the function that you have. Think of that the homotopy classes if you want. If you prefer, you can look at homotopy classes and look at the unique geodesic in each homotopy class.
The problem is about how is E sub mu defined?
How is that?
What is the definition of E sub mu?
Is that you?
Special geodesics.
So it is not homotopy classes, but geodesics themselves.
If you prefer, think of think of a geodesic as represented by a homotopy class first.
But it's hyperbolic metric, so it's unique.
Yeah, absolutely. It's a unique
You can't
geodesic.
have like a family.
No, you cannot have it. You don't have cylinders a lot.
My idea is that you might have infinite number of conjugates classes in the dynamic group in which you have new special geodesics, but it still can happen. right?
Absolutely.
I mean, first of all, it is almost countable to set because it's like somehow counted by conjugacy classes in the fundamental group, but it is still finite. Alright?
Yes,
Because
Because
most of them
they
they
cannot
will intersect.
because they cannot intersect.
Yeah,
Because
yeah.
of the second property, they cannot intersect. So it's really, you have what goes around, you know.
Yeah.
Okay. And no, the fact that is, I mean, I don't know how to.
Point two is the direct consequence of one and two in the definition.
Absolutely. And part one also. If you want. But anyway, yeah. So, all right, so on the left-hand side, we have the sum over this v sub mu is just an index. And it's a finite number of finite set of indices that tells you basically the subsurfaces in which the surface is defined. And then what can we say about the intersection number of a curve and these subsurfaces? So, this one is a sigma v. This is going to be another sigma v prime. And so what can we say about this? The intersection number of the measure restricted to this subsurface with a curve that is contained in this subsurface. Well, obviously, the intersection number is going to be either 0 or non-zero. That's not very, you don't need a big proof for that. However, what happens here is that what one can prove is that it is either 0 or non-zero for all possible curves in that subsurface. That means that once you decompose it, once you find your special geodesic and you decompose your surface, there are some of these subsurfaces that your measure does not see at all. The support is not there. And on the other surfaces, now we see what happens. So if the intersection number with the measure mu is positive for all curves, then there are two possibilities. Well, is the infimum of this intersection number positive, or is the infimum 0? If the infimum is 0, then this is then we have the support of the measure that is exactly one of these that is contained in one of these subsurfaces is actually an invariant lamination, invariant for the fundamental group of that subsurface. And this invariant lamination is surface filling and compactly supported, where surface filling means that the complementary regions are very simple. They have no topology. Okay? And so this is what happens when the infimum, when the systole is 0, or otherwise you can have instead that the systole, that the infimum is positive. And we will see, well, I don't know what we will see. Because what time should I? Well, anyway. And this infimum, otherwise the infimum is positive, and this has all sorts of other consequences. So, okay, that was the systole. So I wanted to mention something about higher Teichmüller theory, and so let's see. I need to cut down what I wanted to say, but let's say that the Teichmüller space, the characterization of Teichmüller space that I want to think of is the one of discrete and injective representations into VS2R, and hence, of course, at some point people started thinking about what happens if you replace VS2R by larger groups. And these people, you can kind of group them by what is the, let's say, what is the group that I want to consider as the target space. So, for example, where we are joint Lie groups, we are talking about the Hitching component, and people who So the techniques were used, the techniques of, Higgs bundles, hyperbolic dynamics, quantum maps, cluster algebra, and the main player in this case were Hitchin, Labourie, Fokke, Goncharov, and I'm not going to, well, by now, as I said, this stuff has become classical, so I'm just saying the grandparents of the thing. I'm disregarding children, grandchildren, stepchildren, whatever, all that stuff, because it's not impossible. And so they looked at this representation, the Hitchin component, that actually, okay, if the surface is punctured, talking about each component doesn't make sense, and then we have possible representations about it. And then with Mark Berger and Anna Hinard, we looked at maximum representations at the same time. We did it with bounded cohomology at the same time as Steve, Brad, Oscar, Garcia, Padre, Guten did it with the Higgs bundles, and this was all following work of Toledo. Then Koziarski we're using harmonic maps. Lately, Marton and Zhang found the generalization of both Hitchin representations and maximum representations. They're called the positively ratioed representations. But I don't know how much they study the geometry of the corresponding Teichmüller space. In any case, the group that is common to the Hitchin component and to the maximum representation is P2NR, and in that case the Hitchin component is actually a strict subset of the set of maximum representation. The equality is actually here where n equals 1 for P2N exactly. Okay, so that's maximum representations. Okay, one reason of looking at higher Teichmüller theory is because Margulis superrigidity doesn't work. So you cannot classify representations the way Margulis did it. And this is because so let's say if you have a representation of lattice into when this is non-compact Lie group, algebraic group, and this is a lattice in a group that is not SO1n and SU1n, then the work of Margulis, Corlett, Ron, Fouché told you how that these representations come from representation of the Endian group, and hence you can the algebraic, and hence you can classify them. However, for example, Raghunathan and Nielsen found representation as subject of lattice in SU1n, they subject onto a free group and two generators, and at that point you can do anything you want. And given that superrigidity is meant to be a tropical the Endian group, that means that there is really no hope for representations of lattice in SU1n to do a classification like this. So that's why it makes sense to look somehow at the representation variety, because you can try to gather more information by the fact that you have more representations at the same time find information about representations themselves. So anyway, given that I'm not to be talking about maximum representation, so the Toledo invariant is what generalizes the Euler number. Can be defined in a variety of ways. Of course, I'm sure that your favorite ways would be using Higgs bundles, and my favorite way is using bounded cohomology. One way or the other, we all start with the same set of representations, and the property is that the Toledo invariant is bounded, and maximum means the representations that realize the maximum value. And all the characterization that I mentioned before of Teichmüller space, they can all be extended to the so-called to the classical higher Teichmüller theory. Of course, with the appropriate caveat, like we cannot talk about any more representative canonical components if your surface has boundaries. I mean, it has functions because the representation variety is one big canonical component. So, but Anyway, one can talk about. So in the previous talk was mentioned the Thurston-Pavot compactification, but before, the first thing that we said was what is the concept of, was to say that if you have a hyperbolization, you can measure geodesics. So you can measure the length of a geodesic. So I have to give you a corresponding concept to that one of the length of a geodesic. So if you take an element G in the symplectic group, then it has eigenvalues. Then in absolute value, you can arrange from the largest to the smallest, and you have only half of them are greater than 1, and the other half are the inverse of less than 1. And then you can define the length to be the sum of the logarithm of the absolute values of this. And this is, of course, positive for the way I chose this. This is not very minor length, by the way. But, so the first thing, if you remember, we said that if you had the UV measure. The UV measure, the intersection of the UV measure with a closed, simple closed geodesic is the length of the simple closed geodesic. Okay? And in that case, the UV measure is given to you. In this case, what we can prove, as Barton-Jean proved it for compact surfaces, and we prove for general surfaces, that if you have a maximum representation, then there exists a geodesic current associated to your maximum representation, such that the intersection of a closed geodesic with respect to this measure is exactly the length, in that sense, of the unique geodesic, the homotopy class of gamma. So this is really the parallel of this result that would allow Thurston to consider this compactification. And here we have a theorem due to Pavot that was mentioned before, that if we take the component of maximum representations, you can found a continuous map with relatively compact image when you take a maximum representation and you consider the length associated to the maximum representation in the sense that we said in this sense here, this length here. And so the relatively compact image also, if you remember before, we said that there was this map from the current into the into the projectivized functions from projectivized length function that to a measure, to a current associates the intersection of a simple closed curve with that measure. And so this was a theorem due to Bonaho, and what one can see is that the image contains the Thurston compactification. Okay? And then at that point, we have this result that the Pavot compactification of maximum representation is containing the image of this current. And at that point, it is important. This is where we realize that we have to figure out, that we have to learn about the composition of current for the composition here of currents. And so if you take a length in the boundary, just like in the case of Teichmüller space, a length in the boundary corresponds to measure geodesic lamination. And here, what we can prove is that if you take a length in the boundary of this compactification maximum representation, then there is the composition of the surface into subsurfaces. And then your length is out of the length associated to a minimum surface filling lamination of a positive system. And let's see what happens in the case when the system is positive. If the system is positive, then what I said before is that a geodesic current that is positive system behaves like a UV current. And this is because on the one hand it has somehow this property, but also there is this theorem that if you take a compact subset of your surface, then there exists constants C1 and C2 such that the intersection of your geodesic current with a simple closed curve is sandwiched between the hyperbolic length of these two, the hyperbolic length of the curve given this time system constant. Okay. And in particular, as a corollary of this, we have that there is an open set of discontinuity in the set of current. So there is a subset of the set of current at the boundary on which the mapping plus group acts approximately discontinuous. And I think I'm going to stop here. Thank you very much.
Okay, so I think we have time for maybe one question or.
So in this maximum representation thing, you had this like Liouville current.
Yeah.
For the original Teichmüller space, that thing kind of didn't depend on the representation.
Aha, that's
So
an interesting question.
does it definitely depend on rho, or is it?
It depends on the representation even in the classical case. Because what you do, you fix, I know, I didn't say it, but it depends also in the, what I said at the beginning is that if you have, okay, first of all, it's convenient that you put a hyperbolic surface and hyperbolic material on your surface, so you do have a hyperbolic material, okay? And then at that point, if you have a hyperbolization, if you have another hyperbolization that gives you a map from S1 into S1, which is rho equivalent, where rho is the hyperbolization. Okay? And so what you do, you have your UV current, but then you also pull back all the UV currents via this map phi. This map phi, of course, depends on your hyperbolization. So there are, for every hyperbolization, there is a UV current that is the one you obtain by pulling back this. Yeah.
So let's thank Alessandra. Any further questions at the coffee break? So let's do a 10-minute coffee break. So we'll start again at 31 past the hour. 10 minutes. Rush downstairs again.
So we have 10 minutes to walk downstairs and go up.
So we're learning a lot, we're getting a lot of exercise.
Сам подписался, ничего.
You speak next to them, not okay, so I'll ask you a question. Here's something I was thinking about stratification.
Ну, если
Depends on the complex.
такого дурака.
Namely, if I change, like, if you change it, so I think it might not, like,
Такой есть жиру, знаешь, если
somehow, like, if you're in the Higgs boson side, you change your complex structure, now you're not a, so you start with a very, now you're not a very, but you're still, like, you're still in stable manifold, so your strata hasn't really changed. It's just the base point, the special things change.
So when you say
Yeah, so that's a.
what might be true, I see.
So like alpha, some component, maybe not component, but think about like
Нет,
types of
только на его
very
этаже.
structures. Some vector
Ради
of the
этого
ranks
приехал. Ой, я не остановил.
and the degrees of those bundles. So that's something